Hi, this is your instructor, Gary Millette. This is ELE 110, Electronics for Technicians 1. This is the fall of 2022, and this is our last topic of the semester, topic number 16, Transistors and Transistor Applications. So let's get started. So we've seen this before as a diagram of the flow of current in a vacuum tube. And again, you have a negative element that's heated up. Electrons tend to boil off of it if you use an expression. And you have a positive plate in there. And what happens? You have a vacuum, so there's no air to resist the flow of electrons. And it turns out the electrons will flow to the anode. So it's a diode vacuum tube conducting current. By the same token, and then what happened? This happened back over 100 years ago. People experimenting with vacuum tubes put some additional elements, which are called control grids at this point, into the vacuum tube. So you might notice that the cathode is there in the center, and there's a flow of electrons off of it, but you see a grid, which is a wire filament that's wrapped around the cathode, and another grid, well, it's called the screen, another wire that's wrapped around that. And what you notice in the diagram is it kind of squints the flow of electrons down, especially if I put a negative voltage on those two grids, as they're called. So those are called control grids, and they can modulate or adjust the flow of current in the vacuum tube. So the first active devices were vacuum tubes, as we've noted before, and here is what's called a triode vacuum tube amplifier. And the triode is because there are now three elements in the tube: the plate, the grid, and the anode or cathode. So as they show in this diagram, they put a small sine wave into the grid. V stands for vacuum tube. That's a symbol for vacuum tube. That's V1, vacuum tube 1. There's an RK for cathode, and there's an RA for the anode. And what happens, I have a positive voltage, V sub A, for the anode. I have a blocking capacitor, C sub 0, which blocks the high voltage, which is on the positive high voltage on the anode, because I don't want to burn out any succeeding components. And what happens is this small grid voltage can cause a larger variation in the output voltage. And again, that's the flow of the current can be controlled by the grid element placed between the cathode and the plate. This arrangement can provide a circuit gain, a small input signal yielding a larger output signal. Vacuum tubes would actually have a characteristic mu, they call it, for the gain, and mu very often is about 20 in a vacuum tube. So you get about 20 times the voltage output as you put in. Again, we're controlling the flow of current. So here we have a picture of a vacuum tube with, again, the anode now is this kind of cylindrical metal plate around the cathode, but between the cathode and the plate there's a control grid. So again, the same notation we have over on the right hand side. The flow of current within the vacuum tube can be controlled by a grid element placed between the cathode and the plate. So what do we use these for very early on? Well, obviously radio and wireless use vacuum tubes, but in about the 1940s, there were very early first computers were built with vacuum tubes acting as switches. So in this case, the vacuum tube either conducted a current, the control grid was not activated, we'll say, or was in the on state, or did not conduct a current, the control grid was activated, made so highly negative that no electrons could make it to the plate terminal, and was therefore in the off state. So vacuum tubes could be used in circuits that stored a 0 or 1, an off or on, low or high voltage, and these types of circuits were known as memory and or registers, or they were used in circuits that form what we call logic gates, which were used to perform computational functions. Now, give you a little more insight about logic gates. Logic gates take inputs and give us certain outputs for certain combinations of inputs. You might want to refer back to PowerPoint presentation number 14. And maybe I'll review that again in this one, I don't recall. So transistors were solid-state vacuum tube replacements, in that just as solid-state diodes replace vacuum tube diodes, or vacuum tubes that is, transistors replace the vast majority of triode vacuum tubes and the different variations of triodes. I didn't mention there were what they call tetrodes and pentodes, which were 4-element tubes. Remember that screen grid was the 4th element, and then there was pentodes. They had what they called the suppressor grid. So there are different types of transistor families. There are BJTs, which stand for bipolar junction transistors, and FETs that are subtypes of these different families. FETs stand for field effect transistors. On this slide, we have just bipolar junction transistors on the bottom left here. So you take a look and use in the top portion of that little picture, there's a PNP device, and it says collector, base, and emitter. So that's a PNP transistor. The symbol for it's down below, and you say that the elements has 3 terminals, much like a vacuum tube, collector, emitter, and base. You control the transistor through the base lead, and you can turn the current off between collector to emitter. Now, by the way, the PNP is pointing in. The little arrow on the emitter lead points in. So that's what's a PNP, pointing in, we'll say. On the right-hand side, we have an NPN sandwich, and it turns out that, again, collector, base, emitter. Down below, it shows the NPN transistor, and notice the emitter now has the arrow pointing out, so we call that not pointing in, and we recall that as being an NPN transistor. Again, the base for that NPN controls the flow of current between the collector and the emitter. So bipolar junction transistors are made up of a sandwich of materials, either NPN or PNP structures. They yield a bipolar junction transistor, or BJT. Now, how do we get N and P-type silicon? Pure silicon does not conduct electricity very well at all. Basically, it's an insulator, hence the term semiconductor for the type of silicon used to make electronic devices. Diodes and transistors are made from doped silicon material, either N-type or P-type silicon. Doping increases the conductivity of the silicon. By the way, the first devices were germanium, and it turns out germanium had a problem with temperature, so it turned out that they went to silicon. It was a better material to work with. To make N or P-type silicon, one adds materials from the other columns of the periodic table of elements. See the next slide. We've talked about this before. Adding column 3A elements results in P-type silicon, and adding column 5A elements results in N-type silicon. So again, we've seen this several times now. And on the right there we say 3A materials yield P-type because there's lack of electrons. 5A materials yield N-type because there's extra electrons. So now we're going to move on to what we call junction field effect transistors. And I say think water hose. So probably everyone has taken a water hose at some time in their life, and they've squeezed the water hose and it stopped the flow of water coming out. You could crimp the water hose over. That stops the flow of water. So let's take a look at these 2 devices on the left-hand side here. Notice that there's a green center one and there's a gray center one. The terminals are called drain and source, the top and the bottom. On both of these, there's a gate to the side, and it turns out there's a gate on either side. So the one on the far left is a P-type channel, which means there's a lack of electrons, but if I took and put a battery between the drain and the source, I'd get some flow of current through that channel. The one on the right is a N-type channel, and again, it's got a drain and a source. I do the same thing, put a battery across the drain and source, I get some flow of electrons through the N-type channel. Now the gates turn out in the green one, I have the gray or N-type material, the opposite material. On the right-hand side with the N-type channel, I have the green or P-type material. So to understand how this works, think about a water hose. One may squeeze the hose to cut off the flow of water, which we'll think about as being current. So for this type of FET, applying a correct voltage polarity to the gate effectively squeezes the conduction channel. So we'll see that in this next slide. So here we have a junction field effect transistor, same diagram as the last page. Notice that I have a voltage, a battery, VDS, and that's voltage drain to source, and the positive is connected to the drain, and the negative is connected to the source. And electrons would flow through that channel from negative to positive. The gate has a battery connected to it, and this only shows a gate on the left-hand side. and there probably would be a connection to a gate on the right-hand side. It's not shown in the diagram, but the gate has a negative potential on it, and what happens is that you notice that the channel is being squeezed. Now, it's like pinching a hose to control the flow of water. Note that a negative potential is what's needed for this example. So if I didn't have any voltage on the gate, I would have a bigger channel. In this case, I put a negative voltage on the, and what happens? When I put a negative voltage, I force electrons away from the p-type material, making a larger effective p-type material and squeezing the conduction channel, and again lowering the amount of current. And I could go from squeezing it so there's totally no channel and I get no flow of current, or I have cutoff, it's called. Here's another type of field effect transistor, and you might notice I've talked about field effect transistors now. Bipolar junction transistors were around for a long time. Most of their activities have been taken over by FETs. This is called a MOSFET, which is a metal oxide silicon field effect transistor. If you look at this one, this is a p-type substrate, that's the body of it, and we still have a source and a drain, and they're n-type. Notice N plus, indicating that it's highly doped N. Then there's a gate, and the gate is separated from the channel region by an oxide, silicon dioxide, which is a good insulator. And the gate is metal. There's metal conductors to the source and a drain, and there's no channel for conduction right now in this device. So for this MOSFET device, a conduction channel can be created in the channel region, where there previously wasn't one, by applying a positive voltage to the gate. If I apply a positive voltage to the gate, it'll repel the p-type material, and electrons will go in there, and I'll form a channel. So a positive voltage will create an n-type channel by attracting free electrons from the p-type material. And once I have a channel, it turns out I can have conduction. So this would be called an enhancement MOSFET. So here it shows how this operates. Notice from source to drain, I have a battery up top, and of course this is a little bit different than one we showed before. The positive was on the source and the negative was on the drain, but here we flip them around. Doesn't matter which direction they are, I'll have current flow through the channel if there is one there. So this shows the positive on the gate, forms an induced N channel. Again, the substrate is p-type, but now I have this conduction from the source to the drain, and I can have conduction of current. So again, this diagram shows what's known as an enhancement MOSFET, or E-MOSFET in operation. A positive voltage from the battery attached to the gate terminal has induced or created an N channel between the source and drain terminals. This channel allows the flow of current. So that shows the operation of a enhanced MOSFET. So what are some of the applications of transistors? Well, transistors, bipolar junction transistors, and field effect transistors are not easy to set up in circuits. I should point that out first. It turns out you have to bias these things, which means putting different voltages on in the bipolar junction transistor, the base, the collector, and the emitter. And the same thing with a field effect. You have to have various voltages, as we mentioned, to turn things on. So it's not an easy thing. We used to spend semesters learning how to bias transistors to make them into, useful things. So here's a block diagram, and this shows a transistor as an amplifier. So in an amplifier, the output's bigger than the input, may be constructed from semiconductor devices. We show a DC power supply, and that DC power supply supplies power to a power amplifier and also to the small signal amplifier. So what you see is a small sine wave on the left-hand side. The increased audio power comes from the DC power supply, and this drives a loudspeaker on the right-hand side. And even though the sine wave is not much bigger there, there's probably a lot more current in that signal on the right-hand side. So that would be an amplifier. We also like to use bipolar junction transistors as switches. So in this one, you see a relay above the transistor. There's a flywheel, in this case called flywheel, not a flyback, or what we called it before. So it turns out that that is to protect the transistor when the relay field gets, collapses real fast. So in this case, you might notice there's a VN, which is a positive going voltage. There's a switch there. says on off, and there's RB for the base resistor. There's another R resistor, and of course, again, you have to figure out what the size of these resistors are to make this work. Then there's what's called the base current, I sub B, and I sub B will induce a collector current, I sub C. There's a voltage V sub E, which is dropped across the transistor, I'll go back to in a second, and beta indicates the gain of the transistor. Excuse me, beta can be 100 to 200. So for this circuit, a positive voltage applied to the bipolar junction transistor device turns it on, and thus applies voltage to the relay, which in turn switches power to the load. The transistor becomes effectively a short circuit. The voltage VCE goes to maybe 0.2 of a volt. So in effect, you have positive voltage up VCC on one side of the relay, and you grounded the other side of the relay. And that fires the relay up. Again, if I take the switch and open it up, and now I don't cause base current to flow, I'll have no collector current. The voltage on the collector will go high, then it'll go up to the value of VCC, and there'll be effectively no voltage across the relay to turn it on. Okay, let's go to the next slide. So what do these things look like? Basically a device like this. Notice there's kind of a heat sink connection on it. There's a metal back to it and a hole through it, so I can take and screw it to a heat sink. And notice there's the 3 leads. The 10 pieces, it's probably diagram came from a vendor who wanted you to buy 10 of these at a time. Let's take a look at a power MOSFET switch. So in this case, it's the DC motor we're going to control, and there's something called a snubber or clamping network, which is very similar. Since we have a motor, there's turns of wire in a motor. We'll have the same problem with a collapsing magnetic field inducing a voltage. We don't want it to burn out the MOSFET, so we take and put a diode there. This one is being driven by a AND logic gate on the left-hand side, and the logic gate is the input to the MOSFET switch. So apparently when the gate has a positive voltage on it, what will happen is it will induce a conduction channel. You might look between D and S in this diagram. There's a dotted line, which indicates there's no real channel there. Only when I apply voltage to the gate will there be a complete connection between the drain and the source, D to S. So what happens, I have an input. Notice that both inputs of the TTL logic gate, the transistor logic gate, are connected to that input. So they both go high at the same time, causes the output to go high, causes the gate to go high, causes the drain to source to act like a closed switch, and causes the motor to turn on. Okay, so let's go to the next one. What do they look like? Same thing. Same packaging as the bipolar junction transistor. And again, we've taken a look at the solid-state relays before, so I won't go over those again, except to just point out that I could have in the top right-hand one an NPN transistor, which I apply a signal to the base, turns the transistor on, so the transistor acts like a short circuit, and I have infrared light put out by the LED in the solid-state relay. So what about ICs? Well, ICs got their start in the 1960s, believe it or not. Wasn't long before op-amps were introduced. Op-amps, simplified amplifier design. A simple ratio of 2 resistors sets the gain. No need to design bias circuits. So this shows a 741 op-amp, been around for decades now, and it turns out that the diagram of it is shown with a triangle with a minus and plus, an inverting and non-inverting input, and pin 7 gets V plus, pin 4 gets V minus, so I could put plus and minus, say 12 volts, plus and minus 15 volts to supply the power to the op-amp. And the output is pin 6. There's a couple other terminals there, offset null, I can take, and there might be a DC voltage coming out of pin 6. I can get rid of that by adjusting the offset null. So it turns out the op-amp, I don't have to supply anything but a couple of resistors, and we'll see that in the next page here. So here's an inverting op-amp and a non-inverting op-amp. The one on the left, I put an input voltage in, goes through Rin, that's the input current. Most of the input current becomes I sub F. Feedback current goes through the feedback resistor R sub F. And if you do the math and so forth here, you get the gain A is V out over V in, which is equal to minus RF over Rin. So if I use the 100K for RF and the 10K for Rn, I'd have a gain of 10. And the only thing that would happen is the sine wave would be 180 degrees out of phase or flipped over. So the one on the right, the non-inverting op-amp, because it goes into the plus input, what happens here is I have RF and Rn again. What if RF was 100K and Rn was 10K? Well, what would happen is the gain would be 10 plus 1 or 11, as shown by that equation here. So it turns out that these are two op-amp applications. So, again, this is review. Op-amps have many analog applications. They can be used as amplifiers, filters, oscillators, summing amplifiers, integrators, differentiators, voltage regulators, constant current generators, I to V and V to I converters, and finally comparators. So I would finish this off by telling you that modern digital circuits are built from CMOS transistors, which stands for complementary metal oxide silicon transistors. Remember, those are FETs. And also modern ICs use surface mount technology and can have entire systems on board the chip. So that's it for this presentation.